Okay, so we're going to go ahead and start what we worked on earlier today in class. So when we graph these exponential functions, it's important to make sure that we go ahead and include at least two negatives in there. So we're going to do a -2, -1, 0, 1, and 2. Okay. So again, when we look at this function right here, we're saying for let's start first with 0. 0 is going to be easiest first. So when x equals 0, that tells us that we plug in the 0 for the x, and we have 3 to the 0 power. Well, anything to the 0 power is 1. So we put a 1 in here. Okay? So now we're going to go ahead and do 1. When x equals 1, then this tells us we plug in a 1 for the x up here, and we get 3 to the first power, which is 3. Okay? When we have x equals 2, then this implies that 3 to the second power, which equals 9. Okay? So when we have x equals -1, this implies 3 to the -1 power. Now remember, this negative power tells us that we are going to flip it and make the exponent positive. So that's just going to be simply 1/3. Okay? And then of course when we have x equals -2, then that is the same as 3 to the -2 power, which when we flip our base, we have 1/3 squared, which equals 1/9. Okay? And notice the pattern. When our x to the equals 2 is positive, we have 9. -2, it's 1/9. We see the relationship here? Okay? You can see that we have the reciprocals of each other when we have negatives or positives in front of the x. So we plot them. We're going to have this -2, 1/9, which is going to be about right there. We're going to have -1 and 1/3, just a little bit above it. We're going to have 0 and 1. We're going to have 1 and 3. And we're going to have 2 and 9. And our graph is going to look a little bit like this. Okay? Now again, we talked about asymptotes. Okay? And this is the line that our exponential function is going to grow closer and closer to, but is never going to actually get to. Okay, and in this case, it looks like, that looks a little bit thick. Hang on. Looks like our exponential graph is coming closer and closer and closer to this line. All right, and so again, we see that we have a +0 right here, so our asymptote is y equals 0. Okay, the y-intercept, which is basically where our graph passes through the y-axis, is always found when x equals 0. So we can see that our y-intercept is at 1, because where it crosses the y-axis here. But we also know that if we looked at this table, whenever x is 0, our y is going to be 1. So our y-intercept is the point 0, 1. Let's look at the next one. Okay, this one has a multiplier out in front. So we could almost go ahead and change this and say, let's, instead of doing 3 times 1/4 to the x. Let's go ahead and do 1/4 to the x here, and then we'll make another column and we will multiply that by 3. Okay, so this is where we multiply it by 3. All right, so let's look at 1/4 to the x. Okay, so again, -2, -1, 0, 1, and 2. Okay, so again, when x equals -2, this implies that we have 1/4 to the -2. Now again, the negative implies that we have to flip the base and make the exponent positive. So that equals 16. Okay, so x equals -1. Well, this implies again that we have 1/4 to the -1. The negative tells us flip the base and make the exponent positive, so we get 4. Alright, x equals 0 implies 1/4 to the 0 power, which is 1. Okay, so I'm going to go ahead and erase this so I can have a little bit more room. Actually, let's do this instead. Nope, can't do that. Okay, so now when x equals 1, this implies 1/4 to the first power, which equals 1/4. And then when x equals 2, this implies 1/4 to the second, which is the same thing as 1 squared over 4 squared, which equals 1/16. Now we'll come through here and apply this multiplier here, which is 3. So we multiply it by 3. So 16 times 3 is 48. 4 times 3 is 12. 1 times 3 is 3. 3 times 1/4 is 3/4. 3 times 1/16 is 3/16. So these are our ordered pairs. -2, 48. -1, 12. 0, 3, 1, 3/4, and so forth. So we'll come over here. -2, 48. Oh, we're out of the scale. We can't really use that point. Let's do -1, 12. We can kind of estimate that 12 will be up here somewhere. Okay, 0, 3. Note that because x is 0, 3 will be my y-intercept where it crosses through. 1 and 3/4, and 2 and 3/16. And we have a graph that looks kind of like that. Okay, and so again, because our asymptote would sit out here, our asymptote is y equals 0. Just like that, if we had this function, but instead of 0, we added a 1, then our asymptote is y equals 1. Okay. Now, one thing that we can look at here is if I have that function that we just looked at, we have y equals 3 times 1/4 raised to the x. Okay, and again, that's the graph that we saw. Okay, if we come back here and look at so this is our graph, and of course if we were just to move our graph next to the one that we're looking at right here, it looks very similar. Okay, our y-asymptote is still at 0 or 0, 3. I'm sorry, our y-intercept is at 0, 3, and our asymptote gets closer and closer to the x-axis. Okay, the reason why I show you this is because if I came out here and now I added a 1, well, look at this. Now, let's move to another page here. So if I came back here and looked at this graph, it's the same function that I had before, but it's coming closer and closer and closer to this line of y equals 1. Okay? And if we go back and we look at, when I add this 1, my asymptote, my whole graph moves up 1, and my asymptote is at 1. Same thing if I had a minus 4. Okay? Okay, again, same thing. Our graph is moving down, and it comes closer and closer and closer to y equals minus 4. Okay, so this just kind of helps you out a little bit with the asymptotes. All right, so this one right here says analyze each table and determine. Let's make sure that we did everything we needed to do over there. Yeah, we did. Analyze each table and determine if a common difference or common ratio. Then determine the graph represents exponential growth, decay, or is linear. Okay, so again, let's look at this. How are we getting from the first to the second term, second to the third term? Well, we are subtracting 10. We are subtracting 10. Okay, so when we add or subtract, we have a common difference, which is negative 10. Okay, now if you think about it, when we did sequences, all right, we knew that if we had a sub n equals dn plus a sub 0. So if I was to back up one position to the 0 term, instead of subtracting 10, I would add 10 to go back this direction, and I would have 60. So then my a sub 0 term is 60. My common difference is negative 10, and I have this explicit rule. A sub n equals 10n plus 60. Now this is a linear function because if I just replace this a sub n with y equals negative 10, replace n with x plus 60, we know this is a line and it is in slope-intercept form, where 60 is my y-intercept and negative 10 is my slope, which means that it is a linear function. Okay, so this next one right here says, okay, well, how did I get from 16 to 4? Well, we know that we divided by 4. Okay, now again, if we divide by 4, if I take 3 and I divide, actually, let's do something different. If I take 8 and I divide 4, well, we know that we have 2. There's no difference if I say 8 times 1 over 4, which is equal to 8 over 4, which in fact still equals 2. Okay, so the reason why we show that is because if we are dividing by 4, we are in fact really just multiplying by 1 over 4. If we are dividing or multiplying, we have a common ratio, which is 1 over 4 in this position. And so we have a exponential. And the way that we know that it is going to be decay or growth is if our f of x values increase or decrease as we go along in the positive direction of x. Since we see that they're decreasing, we are going to have an exponential decay. Now again, think about the explicit rules. If we have an explicit rule, this is a geometric sequence. We would have a sub n equals a sub 1 times r raised to the n minus 1. Okay? Well, we can also say that we have a sub n equals a sub 1 times 1 over, actually, hang on, we're going to skip that part. We're going to skip this part for a second because I don't want to get this confused with something else. Okay, so just note that if we're decreasing as our x's get more positive, we have an exponential decay. We can also determine this by our common ratio. If our ratio is between 0 and 1, then we have decay. If our ratio is greater than 1, we have growth. Okay. All right, so let's look at the next one. The next one, we're using properties of exponents to solve this. So again, because my bases are the same right here, it's just x. When I multiply x to the 5th times x to the 7th, I really have x to the 5 plus 7, which equals x to the 12th. Now again, if I had x to the 5th raised to the 7th power, well, that would be the same as x to the 5 times 7, which is x to the 35. But we know that isn't the case here because we're multiplying the same bases with different exponents. So look at numbers here for a second. If I have a 3 squared times 3 to, let's say the first. Well, that's the same thing as saying 3 to the 3rd power. Well, 3 to the 3rd power is 3 times 3 times 3, which equals 27. Okay, but let's just say this. Let's say we actually figured this out. 3 squared is 9, times 3 to the first is 3, and that also equals 27. So you can see how the rule applies. We're using real numbers. Okay, so that's the first one. So again, now let's look at this. If we have a 5x cubed y squared to the 2nd power, this 2nd power gets applied to each different either variable or number. So I would have 5 squared times x to the 3rd raised to the 2nd times y squared raised to the 2nd. Okay, so 5 squared we know is 25. X to the 3rd raised to the 2 is x. We multiplied these two to the 6th, and y to the 2nd raised to the 2nd power is y multiplied these two, 4. Okay. So in division, if we have same bases and different exponents, we're going to subtract them. So let's kind of break this up for a second. We have 15 over 5, and then we have this x to the 4th over x to the 10th. Okay. Take the 15 over here, the 15 over 5 over here to the side, and we know 15 divided by 5 is 3. But again, keep in mind that we still have this x to the 4th over x to the 10th. If I have the same bases, I will subtract the exponents. Here we added them when we multiplied, but when we divide, we're going to subtract them, and we're left with 3 times x to the 4 minus 10. Okay. So we're going to have 3 times x to the negative 6. Now this negative 6, when we look back at what we did over here, we saw that when we had a negative, we flipped. Let's go over here. We have a negative, we flip the base and make the exponent positive. Okay? So if we come back to this, when we flip the base and we make the exponent positive, this is what we have. So then we would have 3 to the x over 6. Using this same rule right here, this should be pretty easy. It's 2 times x to the negative 9. But again, x to the negative 9 says we flip the base and make the exponent positive. So we have 2 over x to the 9th. Okay? So right here, we're going to have many steps involved with this situation right here. So let's give ourselves a little bit of room. All right, so here we're going to have, when we take this square, we're applying it to the 4 and to the x. We have 4 squared times x squared, which equals 16x squared. Then we have this squared, apply to 3 and apply to the x cubed. So we have 3 squared times x cubed raised to the 2nd, which is 9 times x to the 6th. But again, we got to remember, we're multiplying this by a 16x to the squared. So I'm going to multiply my constants, 16 times 9, which is going to be 144. All right, and then we're left with this x to the 2nd times x to the 6th. And we notice that right here it tells us if I have the same bases and different exponents, I'll add them together. I still have this 144. So my answer would be 144 x to the 8th. All right. And the last exercise here is just simple evaluating a function when we're given specific x values. So if f of x equals 4x minus 8, because we replaced the x with a 2 here, we will replace it in the equation itself wherever we see an x. And so we're left with 8 minus 8, which equals 0. So when x equals 2, f of x will equal 0. All right, so again, f of negative 3, we will plug in negative 3 for x minus 8. So we have negative 12 minus 8, which is negative 20. Now we're going to find f of x, or find x when f of x equals 12. So if we're given this function, f of x equals 4x minus 8. Well, if my f of x equals 12, then I can go ahead and solve for x. So here we'll go ahead and add 8 to both sides. These cancel out. 12 plus 8 is 20 equals 4x. We'll divide both sides by 4. And we have x equals 5. Alright, there we go.